Today we have Chiu from Michigan State. He's his postdoc at Michigan State, and he's doing quite a wide range of physics. And recently he has been working more on the inflation and collider phenomenology of some of these models. And today he will tell us about the sterile neutrinos and light dark matter and their interactions. Let's welcome him.
All right, so thanks for the invitation. So today I'm going to talk about sterile neutrinos and light dark matter. And in particular, I want to tell you that each of them suffers from some problem. But if you're willing to put both of them together, it turns out that they can save each other. So I realized that we have some students here. So when I go through the slides, I would try to be slow. I hope so, because when I talk, I tend to talk more quickly. So slow me down, and if you have questions, just slow me down and ask questions. Okay. So for those students who may not know what are sterile neutrinos, so let me give you a quick introduction. So sterile neutrinos, why are we interested in them, and what are they? So if you look at the experiment lab, if you look at the data, it tells us that the total number of active neutrinos is about 2.99, which means 3. So if you want to add more neutrinos, then that new neutrinos better have to be having no weak interactions. And if they don't have weak interactions, then we call them to be sterile neutrinos. And sterile neutrinos can only be produced through active and sterile mixing. Active are just electron neutrino, tau neutrino, and mu neutrino for those students. And we are talking about adding some new neutrinos. And the question is, why are we interested in this kind of sterile neutrinos? And the reason is the following. There are two experiments. The first one is LSND and mini-boon, and they seem to suggest the existence of EV scale sterile neutrino. Why is that? Let's take a look. So LSND was an experiment located at Los Alamos, and it was shut down in 2001. And the purpose of this experiment was to study the transition probability from anti-mu neutrino to anti-electron neutrino. And what they have observed is a 3.8 axis of anti-electron neutrino events. And if you look at the data analysis, it seems to be suggesting that we need a mass square splitting to be of order EV square. And if you look at the neutrino physics, if you look at all the existing mass square splittings, they are very small. The largest one is only like 10 to minus 3 EV square. So it seems like that you can just use the usual active neutrino oscillation to explain this 3.8 axis. And because of this experiment's axis, so we built yet another experiment which started from 2007 and which was shut down last year. And the main purpose of this experiment is to confirm or to exclude SSND. And they also study this transition probability, and in addition to that, they also look into the neutrino oscillation data. So from the very beginning, since 2007, this oscillation, this transition probability appears to be consistent with what we have observed in LSND. And for years, we have not seen any axis for this transition probability. And at that time, people were wondering why it is so. Because if that has some axis, then this one should also have some axis. But we haven't seen that, not until this most updated paper by mini-boon. So the most updated paper by mini-boon suggests that this transition probability is consistent with that. Both of them have seen some axis. So the question is how to explain LSND and mini-boon. And we have this so-called 3 plus 1 and 3 plus 2 model. For the 3 plus 1, the 3 just means the usual 3 active neutrinos, and 1 is to add 1 EV scale sterile neutrino, and 2 is to add 2 EV scale sterile neutrinos. And before this paper came out, because of the difference between the anti-neutrino data and the neutrino data, So this 3+2 model was much more popular because when you have two strong neutrinos, you can introduce a CP violating phase that can take into account of the difference between the difference between this and that. But then after this paper came out, so there's not much difference between neutrino and anti-neutrino. So 3+1 model became much more popular. But I mean, according to this paper, which does the global neutrino data analysis, it seems like if you're willing to add one more, I mean, although 3+1 model is good enough, but if you are willing to add just one more, the data fitting, I mean, gets slightly better. So both of them are well-motivated models. Of course, there is something that has been swept under the rug, and that is, if you look at these two experiments, they are all called short baseline neutrino experiments. Short baseline just means that the size of the experiment is only like less than 1 kilometer. So basically, we call that to be a short baseline. And for these two experiments, we are talking about the appearance experiment. What do we mean by appearance? It means that the transition probability we are talking about here is measuring the transition probability from one neutrino flavor to another different neutrino flavor. That's what these two experiments are doing. But there are some other short baseline neutrino experiments, such as CDHS, BOJ. They are measuring the disappearance. So by disappearance, it just means that you are measuring the transition probability for one neutrino flavor to exactly the same neutrino flavor. So for those experiments, we don't see any axis. So it seems like there is some tension between the appearance and disappearance short baseline neutrino experiments. So we don't know yet what's happening here. But I mean, people have been even working on 3+3, try to accommodate that, but that still don't work. So we don't know what's going on. But at the moment, just sweep this issue under the rug. I mean, we just need one EV scale neutrino or two EV scale neutrino, strong neutrino. So it seems like that's the end of the story. So you have seen some axis in RSND and mini-wood, and then you just add strong neutrinos, right? But it turns out that's not the end of the story, because there are some bands from the cosmology. In particular, we have the bands from Big Bang nucleosynthesis and the cosmic microwave background, CMB. So from now, I'm going to use BBN and CMB for the abbreviation. And they can measure the effective number of neutrino light relative 6 degrees of freedom. So from now, I call it to be N effective. And in particular, BBN constrains N effective to be 3.3 to 4. And the Planck satellite, which sets a very stringent limit on this N effective, is 3.32. So if you take into account of the error bar, I mean, if you add up 3.32 plus 0.54, it doesn't even add up to 4. So if you have 3 active neutrino and you want to add 1 strong neutrino, it's 4, right? But I mean, adding this error bar couldn't allow N effective to be 4. So it seems like strong neutrinos are ruled out by this cosmological band. Okay.
But you know that it's H dependent state.
Yeah, that's some tricky thing. But the thing is that H dependence, you will need to use other experiments data. So when you combine two sets of data, there could be something tricky. But I mean, basically the Planck satellite, when they close the best fit, they close this. So this even adds the background acoustic oscillation. Yeah. So let's summarize the current situation for EV scale strong neutrino. So it seems like that the short baseline neutrino experiments need the EV scale strong neutrino to explain the data. But apparently this is in tension with the cosmological band on N effective. So we need a way to save EV scale strong neutrino. Okay, so I'm pretty much done with the current status of strong neutrino. So let's keep this conclusion in mind, but then forget about it for a second, because I'm going to move on to light dark matter and talk about what is the possible problem with light dark matter. And then after that, I will tell you why when you put these two problems together, they can save each other. Okay, so now keep this in mind, and then we will move on to light dark matter. So the terminology light has been used in the literature in very different way. But here, when I talk about light dark matter, I really just mean MeV scale. Okay, so and the question is, why are we even interested in MeV scale dark matter? Why? I mean, apart from what I'm going to tell you in a second, I mean, some people nowadays are already talking about like since the direct detection experiments for dark matter have not seen any GeV scale dark matter or higher mass dark matter, and the sensitivity for those direct detection experiments is very low for lower masses. It might be that the MeV dark matter itself is, well motivated for exploration just because of that. But actually, it's more than that. We actually have some more better motivations to study MeV dark matter, because the MeV dark matter annihilation can actually explain the 511 keV gamma ray line observed by the Indigo satellite. And so this satellite is particularly sensitive to the energy range from 20 keV to MeV. And what they have observed is the 511 keV gamma ray line. And I quote this sentence from this paper. The statistical detection significance of the 511 keV line amounts to 12 sigma. Okay, so it's a very strong signal that needs to be explained. And okay, so I guess my next slide would be to explain to you, how would this dark matter annihilation can explain this 511 keV gamma ray line. So it's by dark matter annihilation. So suppose that you have a pair of dark matter annihilating into a pair of positron and electron, and this positron here can annihilate with the electrons in the galactic center, and when they annihilate, they give us the 511 keV gamma ray lines. So for the rest of my talk, I would use this symbol to represent the dark matter anti-dark matter pair, but it's really just a symbol. Of course, if the dark matter is a Dirac particle, it makes sense, but if I'm talking about real scalar of my random fermion, so it just means the same particle, or if this I'm talking about a complex scalar, this symbol really means chi star, but I'm just using this symbol in general. Okay, so I guess this is the main picture for why the dark matter annihilation can explain the 511 keV in gamma ray line. But I guess there's a question coming to your mind, that is, why do we even need MeV? Can't we do like GeV dark matter, or 100 MeV dark matter, or 20 MeV dark matter? Why do we particularly need MeV scale? So let's take a look. So people have worked on these things for in detail in these papers. So what they have found is that if the dark matter is of MeV scale or even heavier, so then the positrons obtained are too energetic to be confined in the galactic center. So that's not good. And at any particular energy, this process will be accompanied by this Brandstrom process. So you produce some extra photons. But if the energy of the dark matter is heavier than 20 MeV, then this process will violate this experiment span, because this experiment is particularly sensitive to the energy of the photons around this range from 20 MeV to 6 GeV. So
actually see an access.
what?
So you could actually see an access method, right?
Yeah, but actually this would still violate that. Yeah. So it sees an access, but if you make this to be confronted with the bands, it would still violate that. Yeah. So and in this paper, so they work out even for more detail. So if the dark matter is slightly heavier than 3 MeV, then when the positrons are obtained from this dark matter annihilation, when it moves from one place to another place, it will annihilate with the interstellar matter, and this will cause some extra gamma ray emissions, and that would violate the COMTEL bands. And this COMTEL is another experiment that is sensitive to 1 MeV to 15 MeV. So at the end, the conclusion is that if you really want to use dark matter annihilation to explain this 511 keV line, then you want a dark matter that is lighter than about 3 MeV.
So your model is chi goes to E plus E minus. So chi is a standard Majorana particle, or this could be any?
I have not specified yet. Yeah. So I will talk about dark matter model building at the end of my talk. But at the moment, we just know the phenomenological properties that dark matter should carry in order to.
So you are assuming this dark matter annihilation to E plus E minus is a S wave process, and that's giving rise to.
You're ahead of me. I'm going to talk about that. Okay. So that tells you why we need MeV scale dark matter. Okay. But then there is actually a very general constraint from the cosmology. That is, in these two papers, they have shown that if you have dark matter annihilation that leads to the correct radic abundance, and if the cross-section annihilation cross-section times the relative velocity between the annihilating dark matter, if the product is independent of V velocity, which we call the S wave, it causes too much suppression to the CMB piece, unless the mass of the dark matter is heavier than 10 GeV. So if you have a dark matter that has S wave annihilation and is of MeV scale, then it's ruled out by CMB. So then the only way for us to have MeV scale dark matter, the only way that can evade this CMB band is to let the annihilation to be P wave. That's the only way it can work. So that answers your question to some extent.
P wave, we know the velocity right now is so small. So still, do you explain that KV line? Like, do you still see the cross section coming out to be?
Yeah, people have worked on that.
And then you go back to the early time that you do.
I mean, P wave annihilation could still. So people have shown that P wave dark matter that leads to the correct radic abundance that can at the same time explain the 511 keV line. And
you can still observe it with enough cross section, because observation needs cross section. So that means you see that cross section now, and then at the whole time the velocity was 0.1 c, and now it's so small. But still it's.
So
order of
the velocity is smaller, right? So this is velocity.
Well, early time velocity was very large.
After freezing out?
No, around that time. So that's the time when you calculate the dark matter content.
Yeah, it's about 0.1 c.
0.1 c. But here it's into a minus 3 c. So
right.
About
So it's suppressed and
4 order of magnitude.
Right, and precisely it's because of this suppression that evades this band, because at the time during the recombination where the CMB photons are generated,
but for the CMB, they're talking about the temperatures at the CMB. That temperature is already low enough to be.
Yeah. So I'm going beyond cutting through CMB. So if you see that, my point is, if you see the signal now, you need certain cross section.
Yes.
And now you feed the cross section with some with this low velocity. And now you go back, you raise the velocity by 2 order of magnitude. That means the cross section or the annihilation cross section goes up by 4 order of magnitude. That explains the dark matter content. So that's a.
Freeze out temperature. Well, that's okay. Well, I think.
Freeze out time.
In terms of his concern on the CMB. So by the time of CMB is already gone, and then it's okay, right?
See, if you explain the dark matter content at the freeze out time, and if you see this signal, this means this line is sensitive to 3 times 10 to the power minus 30 centimeter cube per second.
Well, you can get the cross section, let's say, by
3 times 10 to the
raising the
power
velocity,
minus.
which means you are inside some galaxy or something.
So if, that means you are making some assumptions. So if you don't make those assumptions that there is no boost factor, then the cross section is targeting to see this line
Yeah, this
now.
line has to come from some of the more
3 times 10 to the power minus
concentrated
30.
region of that matter, right?
That I don't know. 3 times 10 to the power minus 30 centimeter to the second.
Well, I just want to say that for CMB time, if it's already frozen out, then you don't have to worry about this.
Yeah, CMB time I don't worry, but the annihilation cross section for like dark matter content and
Yeah, sure. This,
3 times 10 to the power.
You can get a large cross section, and by freezing out temperature, that velocity is larger, and you can get a radioactive density. But that means here, this
Cross section
cross section will be a little bit smaller than the
Not little bit, 4 order of magnitude smaller.
Yep.
And then if you want to have a boost factor, you need 4 order of magnitude. So those are tricky things. So
Sorry. So basically, this slide tells you that if you want MeV scale dark matter, you better let your annihilation cross section to be proportional to V square, which is P wave. Okay. So that's the only way to evade the CFP bar. And there's yet another kinematic constraint, that is, if you have MeV scale dark matter, then that means that the only final states allowed, kinematically allowed, E plus E minus gamma and the neutrino. And in order to maintain the E plus production rate, in order to explain this 511 kV9, usually in the literature, people would assume that the annihilation into the final states of gamma or neutrino to be highly suppressed. So that's just an assumption. Okay. So now.
So I have another question. So your dark matter mass is MeV.
Yep.
So now the S wave contribution comes as M fermion over M dark matter.
Well, not unless you have a model, you
So-
can say that.
So the you P wave like a
Purely P wave. Purely P wave.
yeah, like S wave case, I don't know whether you can build a model where you can.
I have. I
So
mean,
which is a like
in the later part. In the
like
later
you
part.
drop that ME over M dark matter piece.
Yeah. But we are not there yet. Okay. So, but okay, that just tells you. So I have not talked about any dark matter model yet. I'm just telling you that in order to explain this 511 kV9, what kind of properties of the dark matter, if you have a model, should obey in order to offer such an explanation. Okay. So let's talk about the current status of this 511 kV gamma ray 9. So I've argued that we need the dark matter to be less than about 3 MeV, and we want this channel to be dominant, which in other words just means that the dark matter couples more strongly to positron and electron than to neutrinos. And also we need the P wave annihilation in order to evade the cosmology bond.
I have another question. So how sharp is that line?
How short is what?
It's a 511 kV line. It's a very sharp line, or it's
It's
like a
very
line?
sharp. Yeah.
Then you don't have too much freedom in the mass, right?
Well, I mean, you do because the thing is that you will lose some energy in the scanner in the stellar
Well,
medium.
if you have interaction in the interstellar medium, then it will smear out everything to a lower energy, so you get a continuum spectrum from it.
That's right.
And what I'm talking about, okay, you can have a MeV scale mass,
Yeah.
could be 1, could be 2, could be 3.
Yeah.
But in order to produce a very sharp line, it's very unlikely to come from Bremsstrahlung, because Bremsstrahlung will give you a
No, it's not from
spectrum.
Bremsstrahlung.
Or
It's from annihilation.
From annihilation
Yeah.
directly into photons,
Mhm.
then you know the photon energy should match your dark matter mass. And
Well, it also depends on, I mean, your final state. I mean, you have some branch column, you have some other, so that would take
sure,
away.
even a three-body one is is an active photon, so that one doesn't look like a Gramsci. It's actually a very energetic one.
That's right.
But still, you do expect, say, maybe 10–20% or even more smearing of their energy. So,
Yeah,
so if the line is very sharp.
I don't know how
actually
sharp was that. That was a number that I don't remember. But I mean, the significance of this line is very strong. That's the thing. Yeah. So. Yeah. So, and according to this paper that I put out 2 years ago with Bob Scher, so we showed that precisely this kind of dark matter causes some problem. And I'm going to tell you in the next 6 slides why this is so. So for the next 6 slides, I'm going to give you some detailed arguments. And it's more technical, and please be patient and be more concentrated. Otherwise, you wouldn't be able to understand what's going on. Okay, so let's get started. Argument 1. Okay, so it's all about entropy. So, okay, sorry. So from now on, what I'm talking about is the scenario after neutrino decoupling. So in the early universe, neutrinos are in the thermal medium with all other particles, but at some point, when their interaction through the weak interaction is slower than the Hubble expansion rate, then neutrinos are decoupled from the rest of the universe. So everything that I talk about is the temperature below neutrino decoupling, because it's only below that the effect would be significant. So let's get started. So before the dark matter annihilation, so the total entropy of our universe is equal to that. So R is the scale factor of our universe, which characterizes the size of the universe. T is the temperature, and this is the energy density for E plus E minus, energy density for photon, energy density for the pair of dark matter, and the pressure for each of them.
Question. So you are assuming in the thermal bath, now we have photon,
Yep.
Electron,
Yep.
and chi's.
Yep.
Okay. So that means you assume some interaction strength for the chi's, which is not decoupled from the Hubble. So that means it's still interacting with the Hubble.
Sure. It's still in thermal equilibrium.
The thermal equilibrium.
Yeah, it's not freeze out. Yeah, I'm just talking about neutrinos have decoupled.
Okay.
Yeah.
So, but this one did not decouple. So it's interacting with the thermal
Yeah.
background with some, suppose electron or some electron.
Yeah, just like usual thermal dark matter, right? I mean, they become non-relativistic and they annihilate, and then at some point they freezes out. So just typical.
Yeah. But why it's different from neutrinos? I didn't understand that.
Oh, what
Because, neutrino couples to photon
Yeah.
by the electron.
But that's very weak. I mean,
Yeah.
basically so the
And
decoupling
that
happen-
1 MeV comes because if you calculate the interaction rate and compared to Hubble expansion, you find the interaction rate beats or the Hubble expansion rate beats the interaction rate when the temperature is about 0.5. But you put 1 MeV because 2 electron finals, so it's 0.5 times 2, 1. That's why you get 1.
Yeah.
I thought the same thing would be true for your photon or sorry, your dark matter, because dark matter E plus E minus also has some kind of interaction rate.
But I have not specified the interaction yet. I mean, you need to do the comparison of the interaction of the dark matter with the rest of the thermal medium with the Hubble rate. But for the neutrinos, we know it's weak way, GF squared times T to the power 5. We can compare with the Hubble rate, and then you find that the decoupling temperature.
But how can it remain in equilibrium below the electron mass?
Why not? I mean.
How would you talk to photon?
Well,
Electrons say.
I mean, you need a model in order to.
No, it cannot produce the electrons. So photons, what kind of particle you have marked in mind?
You mean the dark matter?
Yeah. So below electrons there is nothing is available, no charge.
No, it's not below. I mean, the neutrino.
Decouple is 1 MeV.
No. This one, when you do the calculations more properly, is about 2 MeV or slightly lower.
Yes, actually it's 1 MeV.
No.
It's not 1 MeV.
No. I mean, that's what I believed in the past. But when you look at the neutrino literature, when they do the simulation more properly, because
so that means now the temperature you are saying is between 2 MeV and 1 MeV.
2 MeV.
You wrote down this equation is whole.
Below 2
but
MeV.
above 1.
Why do you need to?
Because below 1, it cannot produce the electrons. Electron is 0.5 MeV, 0.5 times 2 is 1.
No. Below 1 MeV, electrons would annihilate. This would not be there. Yeah. It will give you some factor.
So
some factor.
This
Yeah.
is not, so this equation holds between 2 to 1. 2 MeV to 1.
Yes. But that would not change my argument, because at the end, if I take this away, okay. So for the temperature below 1 MeV, at the end, what you get is just that when the electron positron annihilates, it just means that you get such a factor. Right. It just get this factor, right? But it does not affect my argument from now on. I know what you're trying to say, but it does not affect. But you're right. Strictly speaking, this formula is only true for the temperature between 1 and 2 MeV. But my argument from now on, it is not affected by that. Okay. So after Kai bar annihilation, so we only have the rest of them. Okay, so they disappear. And now, as you know, for relativistic particles, the pressure is related to the energy density, and the energy density is proportional to T power to the power 4. So when you put all of these guys together, and then you will get this, and when you do simple math, you would know that the entropy is proportional to that. And this GS is the total bosonic internal degrees of freedom plus 7 by 8 times the total fermionic internal degrees of freedom. So for those students, this is nothing special. It's just the usual way when you calculate the energy density for fermions, you get this factor because of the difference between the Boltzmann distribution and the Fermi-Dirac distribution when you do the integral. Okay, so that sums the total internal degrees of freedom. And when the dark matter become non-relativistic, but they are still in thermal. Okay, so they annihilate, but they don't generate any entropy. So their entropy simply transferred to other relativistic particles still in the thermal plasma. So that means that SF, where F here means dark matter annihilation, after annihilation, and I here means before annihilation. So that means that they are the same. So when you equate this, you get this factor. Now, after neutrino decoupling, so neutrinos are not heated up by this Kai bar annihilation because they are already decoupled from the thermal medium. And so their temperature would just go through like redshift due to the universe expansion, which goes is like 1/r of the, this is a scale factor. So when you multiply these two guys together, you know that they are constant before and after Kai annihilation. But since the electrons and positrons or the photons, they are still in the thermal medium, so they are heated up from the Kai annihilation. And so you can do this simple math. That is, you consider this ratio for the photon temperature before and after the Kai annihilation. But before the Kai annihilation, the photon temperature is the same as the neutrino temperature. So I replace this by that. And I multiply this in the numerator and multiply the same thing in the denominator. Okay. And then because of this fact, so this term cancels out, and what remains is this one, which is the ratio of the neutrino temperature to the photon temperature after Kakaba annihilation. And from now on, I denote this ratio to be the ratio with the subscript Kakaba means that it's the factor after the annihilation. And if you go back to this slide, this is the right-hand side of this ratio, which means that the whole thing equals to that. Okay, so that's argument 3. And now, neutrino to photon temperature ratio. So for the dark matter lighter than the decoupling temperature of the neutrino, so all of the entropy from the dark matter annihilation will go into the heating up of the photon. But by this counting, you will see that the ratio really just goes as something like that. So this is the positron and electron, and this is the photon, which gives you 2 polarizations, and this is the dark matter. And if the dark matter is fermionic, you get this factor. If it's bosonic, then you don't get this factor. And depending on whether the dark matter is a real scalar, complex scalar, Majorana, or Dirac dark matter, you get either G equal to 1, 2, or 2 or 4. Okay, so that's something very standard. And 5 here. So what I have told you is that the dark matter starts to annihilate right after the neutrino decoupling temperature. But in general, that may not be true, right? Because I could have a 3 MeV dark matter or 4 MeV dark matter, which means that the dark matter can actually, in general, they could become non-relativistic and annihilate before neutrino decoupling. So in that case, only part of the entropy will go into the heating up of the photon relative to neutrino. So as you see, what I really care here is really the relative heating between neutrino and the photon. It doesn't really matter about the electrons, whether they are there or not. So that's why I said that equation, strictly speaking, is not true below 1 MeV, but the argument does go through it without.
Yeah, but if both neutrino and dark matter decouple at the same suppose 2 MeV. No, I guess even then nothing will change because your delta negative.
Yeah, I mean everything will become more transparent in a second. Yeah. So before, if you have dark matter slightly heavier than the 2 MeV, then before neutrino decoupling, basically because of the dark matter annihilation, both of the photon and the neutrino heat up from this Kakaba annihilation. But right after the neutrino decoupling, the neutrinos are not heat up, but the photons are heat up until the dark matter freezes out at about the temperature, which is about the mass divided by 20. And okay, so now it comes to one of the most important slides in my talk. If you don't understand this slide, then it will be difficult for you to understand the rest of the argument. So let's be more concentrated. So in cosmology, so people try to measure the total energy density of the relativistic particles. This is R means relativistic. So basically, by the time when the CMB is relevant, so basically everything are non-relativistic. Except these 2 guys. It is the photon and the and the neutrino, and everything is calibrated in terms of the photon energy, because in cosmology everything is calibrated with respect to the photon. So you measure the photon, is really the photon that you can measure precisely. So this is where the N effective that is defined. So this factor really just comes from there. I said when the electron and positron, when they annihilate, they will get this factor. But now, so without the Kakaba annihilation, so you have this factor, which is the standard one, and then when you try to extract this N effective from cosmology, so without dark matter annihilation, the N effective inferred from CMB will be the true value of number of neutrinos. But if there are Kakaba annihilation, this factor is actually replaced by the same factor multiplying the difference between the neutrino temperature and the photon temperature after the Kakaba annihilation to the power 4. That means that when you try to use cosmology, when you try to use the data to infer N effective, the N effective that you have observed has actually absorbed this factor. But as I have just told you that if you have dark matter annihilation, then this neutrino temperature will be smaller than the photon temperature because the dark matter annihilation heats up the photon but not the neutrinos. So this is less than 1, something less than 1 to the power 4. That means that if you have dark matter annihilation, it will somehow cause a reduction in the N effective that you can observe from CMB. And the question will be whether this is acceptable. So let's say if we are just having 3 active neutrinos, and you can look at this plot. So the N effective and the mass of the dark matter divided by the decoupling temperature, which is about 2 MeV or slightly lower. But if you can see, if you can take 5 here, because TD is 2 MeV, you can take 5 here, which means that and go upstairs and then go this way. That means that for the N chi less than 10 MeV, you would imply the N effective to be less than 3. So that's the problem. So and not even to mention that we require an N chi less than 3 MeV in order to explain this 511 keV gamma ray line. So that's the problem. So after going through the whole argument, I finally showed you that that's the problem with the MeV dark matter. So now we can take a step back and see what I've told you so far. So at the very beginning, I told you something about sterile neutrino, and it seems like the short baseline neutrino experiments, LSND and mini-boon, require us to have at least one EV scale sterile neutrino to explain the short baseline neutrino experiments. But it seems like this is in tension with the CMB and BBM band on N effective. And the reason is that by adding sterile neutrinos, that makes the N effective to be too big. And for the MeV dark matter, for precisely this kind of dark matter, which can explain the 511 keV line, it is ruled out by the effective number of neutrinos. The reason is that by having this kind of dark matter, you will make the N effective to be too small. So for neutrino, sterile neutrinos, you are making N effective to be too big. For the MeV dark matter, you're making the N effective to be too small. So the question is, why don't we put them together? Maybe when you put them together, I mean, things may just get right. Okay, so let's see. So let's see, if you are willing to add to the 3 active neutrinos with 1 EV scale sterile neutrino, according to this paper, and you can look at this plot. So this line is the color here corresponds to the color of the curve. So B means bosonic. So GB equal to 1 just means that the dark matter is scalar, and this is the Majorana dark matter. This is complex dark matter. This is Dirac dark matter. Okay. So now you know what are these curves. So you see, if you look at so this is the N effective best fit from Planck satellite, which is 3.32. So look at this line, okay, here. So it seems like if TD, I mean, we have some uncertainty in TD, right? So if it's slightly less than 2 MeV, then it's possible that for the M chi to be less than 3 MeV or around that range. This complex scalar dark matter or Majorana fermion dark matter can allow you to have the correct N effective. And for this Dirac dark matter, it might be slightly too high, the mass, in order to explain the 511 keV dark matter. But if you really just want to save the neutrino, the sterile neutrinos, then the Dirac dark matter is still fine. Okay, so this is the case with only 1 EV scale sterile neutrino. Let's try the case with 2 EV scale sterile neutrino. So if you have Dirac dark matter, it seems to be fine. And
I'm sorry, what's the difference between this one and the
Oh.
previous one?
this one has only one EV scale sterile neutrino. This one has two EV scale sterile neutrino. Okay. Yeah. So it seems like that scalar dark matter has no way to get the correct and effective because the best fit is 3.32, which is represented by this dashed line. And so for the case of two EV scale sterile neutrino, the Majorana fermion dark matter and complex scalar dark matter is also fine, and the Dirac dark matter seems to be also fine. And okay, let's skip this. Okay, so the temporary conclusion is that sterile neutrinos and light dark matter can save each other because when you put them together, you can make the end effective to be correct for each of them. And so you have seen this already, so I don't have to talk about that. I just want to remind you that what are the problems, and now they have saved each other. Now, if you are familiar with the sterile neutrino literature or the Planck satellite, the collaboration, if you have read that paper, I think you should ask the following question. That is, what about the upper bounds on the summation of neutrino masses? Because, I mean, the total number of neutrinos is an issue, but the total band of the neutrino masses is also another important issue. So if you look at the Planck satellite, what they are saying is that the total summation of all the possible thermalized neutrino species has to have mass less than 0.28 eV. Now let's look at the global best fitting by this paper. So if you want to add one sterile neutrino, that is 0.93 eV compared to that number. Okay, and for 3+2 model, if you add up these two guys, it's about 1.3 eV, which is much bigger than that. So now the question is, how can we save this? So far, I've shown you that sterile neutrino and MEV dark matter, they save each other, and of course that means that the MEV dark matter saves the sterile neutrino for making the correct and effective. But now it seems like we have a very stringent band on this summation of the summation of the masses. So electoral question would be whether my scheme of MEV dark matter annihilation could at the same time save the sterile neutrino from this band. So let's look at that, and the answer is affirmative. Okay, so when you look at the upper bands on the total sum of neutrino masses, it's really the bands on the non-relativistic neutrino energy density. So depending on whether you have one EV scale neutrino or two EV scale sterile neutrino, you would have summation from 1 to 4 or 5. And N mu I here is the number density for that particular neutrino. And because we are talking about non-relativistic neutrino, so the energy, originally this is energy, but it's dominated by the mass. So that's the non-relativistic neutrino energy density. So when you put this in, you will get this. So I try to, because in cosmology everything is calibrated with respect to photons. So I try to put it in the way that you are calibrated with respect to photons. But the photon temperature to power 3 is proportional to its energy density. So this is very simple, right? When you put this in, and then you get that, I divide everything by T gamma to power 3, and then you multiply everything with T gamma 3. And then if you put that in, so you get this expression. So if the temperature of the neutrinos is exactly the same as the photon temperature, then when you use the cosmological data to set a band on the neutrino energy density, it would give you the true upper bound on the, because when you set this to be the same, so when you use put a band on that, you will get the true band on the total summation of the neutrino masses, right? But if this is not equal to 1, then when you put the band on the total energy, total non-relativistic neutrino energy density, when you say that the the total band on the summation of the neutrino mass is less than 0.28, you're actually putting a band on this whole expression. Well, this is the true sum of the neutrino masses. So let's define. So this is the same as what you just saw here, but I just want to define this symbol. I call this whole thing to be that. Okay. And the question is, what is this? So this factor is equal to that. This 4 divided by 11 comes from there when electron annihilate. And this comes from dark matter annihilation. So now, just to remind you that in the 3+1 model, we have the true summation to be 0.93, and the 3+2 model, we have this. Okay, so let's look at the plot. Okay, so this is the plot with only one EV scale surround neutrino. Again, this is scalar dark matter. This is Majorana fermion. This is complex scalar. This is Dirac dark matter. And as you can see, everything below this dashed line is annulled by the cosmological band. So everything below here, so that means that scalar dark matter is impossible, and the Dirac dark matter and Majorana fermion and the complex scalar are fine. And then if you look at the case with 2 EV scales around neutrino, then you see that we want everything to be below 0.28. Then that means that none of this kind of dark matter annihilation can save the life. So basically, the band on the sum of the neutrino masses basically rule out the possibility of 3+2 model, but 3+1 model is still fine. Okay, now, so for the rest of the 5 slides, Pascal will be very interested because you have been asking me this dark matter model from the very beginning. Okay, so since, as you have seen here, so dark matter annihilation is very good at saving the life of neutrinos. So it would be very natural or very interesting to explore, I mean, what kind of dark matter that can do the job. So let me remind you what we have got so far. So as we know, we need the MeV scale dark matter to explain this 511 keV gamma ray line, and we want the dark matter to couple more strongly to positrons and electrons than to neutrinos, and we want the dark matter to have the P-wave annihilation in order to evade the CMB band, right? And the 2 the case with 2 EV scale surround neutrinos cannot be saved by MeV dark matter, so we are going to ignore that from now on. But as we have seen through my analysis, so if you don't care about the 511 keV gamma ray line, so Dirac fermion is okay to save the line of 1 EV scale surround neutrino. But if you do care about 511 keV, then it seems like only these 2 possibilities are annulled. So let's just focus on this case. Okay. So what kind of dark matter would be possible? Well, these are some very motivated dark matter model. So in particular, you can let the dark matter have electric dipole moment or magnetic dipole moment, which goes like this way, EDM. So sigma mu nu is just the commutator of the gamma mu, gamma nu, and the dual of the electromagnetic field strength. And these 2 models, now let's look at the Annihilation Mod Channel. So for the magnetic dipole moment, see, if you look at these annihilation channels, you don't get anything that is proportional to V square, so it's not viable for our purpose. But this one may be viable because if you see here, this is proportional to V square, right? So by tuning the parameters here, you can make this to be dominant in the early universe, such that this is responsible for the correct radiant abundance. Okay, so this may work, but the problem is the following. Because as I have told you earlier, we want the Majorana fermion. But a Majorana fermion cannot acquire EDM. Do I need an explanation? If you want to preserve CPT invariance, the Majorana fermion cannot acquire EDM. The reason is that the Majorana fermion is CPT conjugate. So under CPT, Majorana fermion becomes itself. But under CPT, the interaction energy for the electromagnetic dipole moment flip a sign. So you cannot have a particle which under the CPT that has a positive interaction energy and at the same time you have the negative energy density. So that violates the CPT. So that means that, well, apparently this seems to be working. But if you are confining yourself to Majorana fermion, then this will not work. So, well, we can try another one. We can try NR dark matter. Okay, so so this is the work that I've done with Bob Scherer. So you can write down this effective operator. So and this is the coupling constant. This is the cutoff scale. Okay, so you can try to work out the NR dark matter and see what are the cross sections. So this is good. This is precisely what we want. And at the very beginning, I've said that we actually want this to be naturally suppressed. And you see, we don't even need to tune anything. It is 0 at the tree level. And the reason that it's 0 at the tree level is that if you go back to this operator, this is the current. So the NR dark matter only coupled to the external electromagnetic current. And when you have the final state to be photons, you have electromagnetic fields, you don't have electromagnetic current. So that explains why it is 0. But unfortunately, we want MeV scale dark matter. And you and I have worked out this. It seems like MeV scale NR dark matter is ruled out by the LC. So
So how about two Majorana fermions?
two Majorana fermion? What you mean Chi1, Chi2?
Chi1, Chi2.
Well, I guess that, I mean, the LC band will still work, right? It's not a matter of you have how many particles, right? It's really the energy.
But you can go with the dipole.
No, but I mean, dipole is, I mean, it's not Majorana.
So it is not decaying.
No, it's two fermions with a mass gun.
Oh, you want decay?
Yeah, he wants to have a decay.
Then I'm not sure if you can explain that 511 kV. Yeah, I mean, it may work, but
no,
you have to.
You can fit the mass gap with the 511 kV.
That might be possible. Yeah, with some tuning, that might be possible. Yeah. But anyway, I mean, my point of doing things here is that I haven't found a real model that's working at the moment. Yeah.
Use the mass gap.
Yeah, maybe that would work. But anyway, for model builders, including myself, we can think about it. So, and then the final conclusion is that I have shown you that the strong neutrino and light dark matter can save each other, and these arguments I have already made. And do you want me to go through that? Probably no. Okay. So, and it seems like the EDM, MDM, and NR dark matter may work, but not. And we need to find a viable dark matter model such that it can save the strong neutrino and at the same time it can explain the 511 kV gamma ray line. Okay, so that's the end.
There's a comment that 3+1, there's double Chiu data last year, and for 3+1 star neutrino, you really have to tune up the mixing or the CMF. And that is making the 3+1 looks a bit less interesting. Because
really?
it's a very large mixing.
Large mixing?
Large mixing and from smaller mass. Yeah, something like this.
Okay, but I mean, one data set cannot.
I have a plot here.
I see. But wait, but one data set cannot change everything.
It's a combined plot.
Combined with all other.
Yeah. No, there's a global fit, and there's a double Chiu data that's not inside the global fit. So if you put this together, this double Chiu is really cutting off quite a bit of the time.
So what's the delta m square?
I think that is about 0.3 eV squared.
0.3 eV square.
Has to be below that, and mixing angle larger than 3%.
Okay. Yeah, it would be interesting.
That's not the most interesting part of the parameter space. So it's not that yet, but it's kind of a get more space.
I see. Yeah. But anyway, I mean, most likely we are gonna need at least one. Because I mean, even the cosmology is suggesting something bigger than 3. Not exactly 3.
Maybe it's for like dark matter.
Yep. So.
Okay. Any other questions?
Yeah. So I guess that mass gap decay probably may not work because you will require the decay to be
I don't really mean that
to be less than the age of the universe. By that rate, I'm not sure if you can reproduce the.
Yeah, you can. Because we recently showed that 1 keV light can come from a 1 GeV. I don't know whether 1 MeV with a 511 keV, probably it would happen before, like
this energy is larger, so the decay rate is going to be a lot faster. So it's dependent on the mass.
Yeah, but you can tune the parameter.
But you can tune the parameter space so that there's
decay can be controlled.
And reduce the.
Decay can be controlled with the couplings. Since you are looking for a model, we can give you the model.
I see. Wait. So if you have so you will still have MeV scale dark matter.
Yeah,
and you
then
have another
all I
one.
do is keV with tinkering the coupling.
Okay. And okay, so
And the mass is how close it is.
right. So you may be able to explain the 511 keV. So now the question will be, could you behave in similar way that you can save the life of sterile neutrino?
Yeah, because the same way, because the 1 MeV, so there are 2 guys close by. Both of them are dark matter candidates.
Okay.
And both of them would, so your equations would be modified a little bit here and there, but nothing much. And then take the ratio, and then sterile neutrino piece is different, because as you say, dark matter is heating up the back.
Right.
And that part dark matter would do. It doesn't matter whether you have one of them or 2 of them.
Okay.
So the heating up mechanism is going on, and then sterile neutrino will come.
It would change the okay. So the heating part will probably go through, but it will change the picture slightly because when you have the out of equilibrium decay of the dark matter, you would generate the.
I have 2 of them. That's it.
It doesn't matter, but the thing is that you would generate entropy. So some of my arguments there would change.
No, same. All I care about that interaction rate. That means you also generated entropy.
No, I don't.
So how like?
It's just that the dark matter become non-relativistic.
It's the same thing would happen in.
Okay, so it's in thermal equilibrium, but it's
non-relativistic.
Okay, that would work.
Because whatever you have done, one can do it just having 2 of them, and one decays into the other by some penguin diagram, for example. That's what.
I see. Okay, that might work. Yeah. Maybe you guys can add a discussion in your paper.
Which paper?
I mean, it seems like.
Oh, thank you.